Let's try some practice. We've got a 25 microcoulomb charge traveling at 150 meters per second to the north, entering a uniform B field with a strength of 0.050 Tesla, pointing to the west. Okay. What's the problem? What will be the magnitude of the magnetic force acting on the charge? So we're looking for magnitude of the force acting on the charge. And which way will the charge be deflected? There's your hint. Make a sketch. Try it out. Pause the video. Then here we go. All right, so we are dealing with a particle. So we're going to use the particle equation. F equals QVB sine theta. In this case, theta is 90. Take sine of 90 and we're going to get 1. That's good. So we get, plug in 25 times 10 to the negative 6 because micro is times 10 to the negative 6. 150 meters per second, and then Tesla stays the same. And there we go. For B, we're going to use the right-hand rule for charges. Note Q will deflect upward. So if it's moving upward, then the flow of the charge, the current is going up. The B field is going to the right, and then it's going to come out of the page. The force will come out of the page. All right, explain why the magnetic force cannot change the magnitude of velocity of the charge while it's being deflected. Sorry. Done? F is not perpendicular to V. Only velocity's direction will change, not its magnitude. A quick review of circular motion. Circular motion. To have circular motion, you have to have a tangential velocity and an acceleration that is exactly 90 degrees. It has to be perpendicular to it. If it's not exactly perpendicular, you're not going to end up with exactly a circle. So in order to have circular motion, these two need to be perpendicular. As the particle moves in this direction, downwards, then our velocity, our tangent velocity, changes direction. Another way to remember this is you have two types of acceleration. You have tangential acceleration and you have centripetal acceleration. Tangential can change your speed. Well, that's not how you spell speed, Mr. Scapetus. And then your centripetal is going to change your direction. So what is tangential acceleration? Tangential acceleration would be if you had an acceleration vector pointed in the same direction as your velocity. That would mean you're either speeding up or slowing down. If you think about it as a car, when you go into a curve, when you go into a turn, you slow down before the turn, you make the turn, and then you speed up. Well, if you are speeding up as you go into the turn, then you're going to kind of skid off to the right. Because your speed is changing. You're speeding up as you're turning. So you're not going to make that nice circle that you need to do to make that left-hand turn. So now on to part D. How do you know that the charge is going to be in uniform circular motion? Well, it's because the force is perpendicular to the velocity. So that means your acceleration is perpendicular to the velocity. That means you're dealing with a centripetal acceleration, therefore a centripetal force. If it were tangential, it would be parallel. It would be in the same direction. You'd be dealing with theta 0, sine of 0. So V is constant. Q and V and B are constant, and so is F. F is constant, so is A. A constant acceleration, perpendicular to the charge's velocity, is the definition of uniform circular motion. We learned about that in a different part of the class. Still dealing with the same situation. Part E, if the charge has a mass of that, what will the radius of its circular motion be? So a fun fact, this is actually how masses of particles are detected. Sending your particle through a magnetic field is going to deflect it. some radius. If you have a massive, let me get a quick B field here going into the page. If you have a massive charge, then that charge is going to go through here. Let's say the charge goes in this direction, so what direction is our force? Force is up. Then this would be deflected like this. Or it could be deflected like this. If it travels a farther away, that would be how massive it is. So that's how masses are detected. That's called a mass spectrometer. Spectrometer. So what's the radius of its circular motion? So we're given a mass. Now we need to find out the radius of the circular motion. So we're going to have to use those circular motion equations. So we found F equals that. We can use A equals the net force, F over M, to get our acceleration. And we know the charge is in uniform circular motion, so centripetal acceleration is just V squared over R. Solving for V, we get A times R, and the square root of that is going to be 2961, or 3,000 meters to 1 sig fig. Consider a charge Q traveling at a velocity in the magnetic field shown here. Show that R equals M times V over Q times B. So the show that command term is giving you the answer. There's your answer right there. Where did it come from? You better look on that equation page and try to find any equation that has these variables in it. And because we're talking about a charge and a magnetic field, my eyes are going right to that 5.4 equation section. Because V is out of the plane and B points out towards you, V and B are perpendicular, so sine of 90 will equal 1. So the force on a charged particle equals QVB, straight from the equation sheet, right? We remember that F equals mass times acceleration, so QVB equals mass times acceleration. Don't forget that F equals F. Forces will always equal forces. So no matter what force we're dealing with, we can have a magnetic force equals a centripetal force. Absolutely. We can have a magnetic force equals a gravitational force for some weird reason. Absolutely. Any of the specific forces, let's say magnetic force, and we need to look at it. Whoa. Let's say we have F magnetic force, and it's the spring force, negative kx. That's absolutely allowed. I'm sorry if you're getting motion sickness from this, by the way. I don't know why it does that. So, now where does the R come from? It's circular motion. A equals V squared over R. So QVB equals M times V squared over R, solving for R. So you need to show every single one of these equations. Have this, have this, have this, have this, have this, and then have this. That'll get you all your points.